This video will review the first part of Chapter 5, introducing the basic concepts of statistics, which you will need later in Chapter 6 when you apply these to evaluating statistical hypotheses. Let's start with an introduction to proportions and distributions. A proportion is just a share of some items considered in comparative relation to the whole population. This is given as a ratio or a fraction. So here's a jar of marbles, and let's say we want to know the proportion of red marbles in this population. So we can give this as the fraction, with the numerator being the total number of red marbles and the denominator being the total number of all marbles in this population. So let's say in this particular jar of marbles there are 60 red marbles, and then the jar contains a total of 100 marbles of all colors. Then the proportion of red marbles will be 60 over 100, or 60%. Proportions are important, and they're typically given in statistical settings with respect to values of a variable. A variable is in statistics is a technical concept and has a very specific meaning. It means, in the case of statistics, it's a general property that may instantiate in different values. A variable must meet these two conditions to be a variable in statistics. The variable values must be they must be mutually exclusive, meaning that there can be no overlap between the values. So mutually exclusive means that no member of the population has at the same time two values of the same variable. I'll give an example of that in a second. The second condition is that the values must be collectively exhaustive, meaning that every member of the population must exhibit some one of these values. Or in other words, if you pick out all the members of the population which possess a value for that variable, for all the values of the variable, then you will have picked out the entire population. So let's go back to the jar of marbles here. Notice that these are all solid color marbles. And so we can use, for this particular population, we can use the variable, let's call it color. And that variable, color, has these 6 values in this case: blue, red, green, yellow, black, and white. The variable color values are mutually exclusive because each marble is completely and totally just the one color value each. See, these are all solid color marbles. There's no marble in here that's, say, half red and half black, or half green and half yellow. They're all 100% just the one color value each. To put this another way, if you know that a marble is, let's say, green, then by virtue of that, you also know it is not blue, not red, not yellow, not black, and not white. The values for the variable color in this particular jar of marbles are also collectively exhaustive, since if you were to remove all the blue marbles, all the red marbles, all the green marbles, the yellow marbles, black marbles, and white marbles, then you'd have an empty jar. You'd have removed all the marbles in the jar. That's another way of stating that these color values are, for this population, are collectively exhaustive. So for the same jar of marbles, we can exhibit many different variables, each variable with a separate set of values that must meet the two conditions of mutually exclusive and collectively exhaustive. in other words, there are many ways that we can divide up the same population, that same jar of marbles. We can divide up the marbles in there, say, by location, top of the jar, bottom of the jar, left of the jar, right of the jar, so forth. We could divide them up by size, large, medium, and small. We could divide them up by shape. We could divide them up by orientation, texture, and so forth. You get the idea. For some variable, if we give the proportion of the population for each value of the variable, then we will have given the distribution. So forget about the jar marble I just showed you in the picture in the slide. Let's imagine there's some new jar of marbles. In this new jar of marbles, there's just 3 colors: red, green, and blue. And let's say that I describe to you the proportion for each color, where I say, in this example, say 25% of this jar has green marbles, 25% has blue marbles, and 50% have red marbles. And notice that adds up to 100%. So that's collectively exhaustive. I've described all the marbles in the jar by giving the proportion for each color value. And in doing so, I've given you the distribution. That's what we mean by distribution. So if somebody asks you for a distribution for some variable, then you list a proportion for each value of that variable until you've described 100% of the population. The next important concept is that of correlation. This is very important for evaluating statistical hypotheses. If two things are correlated, let's say 2 variables are strongly correlated, this means that knowing something is true with the one variable gives you good reason to expect something to be true about the other variable. If there's no correlation, then knowing something is true about the one variable doesn't give you any information whatsoever about what may be happening with the other variable. So if 2 things are correlated, it means the two variables are correlated. It means that the 2 variables exhibit a relationship of interdependence. For instance, we see a positive correlation between A and B, let's say 2 variables A and B, if whenever A goes up, B also goes up. And when A goes down, B also goes down. That's a positive correlation. They move up and down together. We see a negative correlation between A and B if whenever A goes up, B moves in the opposite direction. B moves down. And whenever A goes down, B goes up. So negative correlation doesn't mean zero correlation. It means the same level of, or can mean the same level of strength of correlation. It can mean there's a strong correlation between the 2 things, but in the case of a negative correlation, it means they move in opposite directions. But they're still interdependent. And that's something that you should remember there. All right. So people often get confused about the distinction between correlation and causation. Do not get these 2 confused, and it's very important for what we're going to do in Chapter 6 and beyond, that you understand very, very clearly that correlation and causation are 2 separate and distinct ideas. The famous sentence here is that correlation does not entail causation, or correlation does not necessarily imply causation. 2 things can be correlated, but their being correlated doesn't necessarily tell you that there is a causal relationship or what kind of causal relationship. Okay, so let's take a look at these kitties here. The kitties in the picture are looking guilty because they're holding a bag of Cheetos and they have orange dust around their mouths. And holding a bag of Cheetos and having orange dust around your mouth is strongly positively correlated with having eaten Cheetos. Does this mean, though, necessarily that the kiddies are actually guilty of eating or having eaten the Cheetos? Could they, in fact, be innocent? Is that a possibility? Well, perhaps. Probably not in this particular case. Here's a good example of correlation not having anything to do with at least a direct causation. There are a group of misinformed people who believe that because childhood, and I stress this is the reasoning here, they believe because childhood immunizations are correlated with an increase in the diagnosis of autism, then therefore the immunizations must be the cause of the autism. So they're thinking there's a correlation, therefore there's a direct causal relationship. However, many of these same people probably also are consumers of organic produce and believe that to be that organic produce to be healthy for their children to eat. Yet, yet the same correlation, a relationship between organic food sales and autism is also true here, where you see this line here representing increase in over time, an increase in the number of diagnoses of autism, is very closely aligned with this other trend of an increase in organic food sales. Very closely related to each other. They have in fact a very high positive correlation with one another. Yet, although we see exactly the same correlation between organic produce consumption and diagnosis of autism, few of these people would conclude the same sort of causal relationship they assert of childhood immunizations and autism. In other words, few of these same people would think that the organic foods are causing autism. Yet, the relationship between organic food sales and autism is identical, if not stronger, than the relationship between childhood immunizations and autism. So this, in other words, is a counterexample to that erroneous way of thinking. In the next slide here we see a pretty silly example, but illustrative, is that right? Illustrative of the same principle that correlation does not entail causation. In this case we see a negative correlation. That is, as in this case we see, okay, the one variable here is global temperature. So as global temperatures are going up over time, the number of pirates goes down. So we have a negative correlation. The one goes up, the other goes down. But we are not going to conclude that the pirates were killed off by the higher temperatures. That's silly, and the reason it's silly is that correlation does not entail causation. Okay, I think you get the point. Now, while correlation never entails causation, the other way around, causation nearly always implies correlation. Almost always. There's some very special technical cases where it won't, but almost in every practical case, practically almost always, causation does imply correlation. So one way of thinking about the relationship between causation and correlation is that correlation is a clue to causation, but not a guarantee. If A and B are correlated, it could mean one of four things. Either A is causing B, or B is causing A, or A and B are, actually there's a mistake here, A and B are the common effects of C, or A and B are not causally connected at all, and this correlation is just a coincidence. Sometimes, and for this last point, sometimes an apparent correlation among one sample group will later disappear as we increase the number of samples. This means that the original apparent correlation was just a fluke. In terms of how we will utilize correlation in our textbook, we will show a distribution of two variables in a population using these sort of rectangles that you see here. On this slide, each rectangle, there are three rectangles, 1, 2, 3. Each rectangle represents a different population of marbles. So you can think of the three different rectangles as each showing a different jar of marbles. On this first rectangle here, you see two variables being represented. Across the top, you see the variable color with the two values red and green. On the side, you see the variable size with the two different values small and large. This jar of marbles, we can infer from the information contained in this rectangle, this jar of marbles has only two colors and two sizes. There are 100 marbles total in this jar. By color, this group of 100 is divisible into 60 red marbles, 40 green marbles. By size, this same group of 100 marbles is divisible into 25 small and 75 large. Given those numbers, and assuming probabilities according to proportions, there is a 75% chance of picking a large marble at random from this jar. So regardless of color, based on these numbers, there's just a 75% chance of picking a large marble. In this lower left quadrant here, you can see that 75% of the red marbles are large. In the lower right-hand quadrant, you can see also that 75% of the green marbles are large. Now in absolute numbers, 45 of the marbles are large reds, and in absolute numbers, 30 of the marbles in this population are large green. And though these absolute numbers are different, it is the proportions that interest us. There is an equal proportion, 75% each, of large reds and large greens. And notice that these horizontal lines here, these horizontal lines, look like one long continuous single line all the way across. In fact, this is actually two separate horizontal lines. This is one horizontal line here that's showing you the large reds, well, from this one direction anyways, and on the other side we see it is a separate horizontal line showing you the large greens. And it just so happens that because each proportion, large red and large green, happens to add up to 75%, the same proportion, that's what's making these two lines look like one continuous long single line all the way across. And this is important because visually, this is what zero correlation looks like, or no correlation looks like, for these, at least for these textbook examples. Anytime these two horizontal lines position in this way to look like one continuous line all the way across horizontally, it means zero correlation or no correlation. So imagine now that I'm off in another room with this jar of marbles. You cannot see me. And I'm going to pull at random a marble from this jar. And you're trying to guess whether I will pull a large marble or not. If I yell out to you, "I pulled a red marble," from the other room, is this information going to help you at all in your estimation about the probability of whether or not I pulled a large marble? No, it will not. Since I pulled a red marble, as I just told you, then you will know there's a 75% chance that it's a large marble. But if I had pulled a green marble, it would also have been a 75% chance. And regardless of color, it's a 75% chance. So telling you the color makes no difference either way. In other words, telling you the color of the marble in no way affects the chance that it is large. It does not change the probability that you would assign to its being large. And this is exactly what we mean by zero correlation. Intuitively, if we are interested in the proportion of large marbles, it does not matter whether we look among the red or the greens, because the proportion is the same in either color. Now let's look at this second jar of marbles here, represented by this next rectangle. In this case, we have 60 reds, 40 greens, but now we have 45 small marbles and 55 large marbles. By proportion, 75% of the reds are large. Here, 45%, and that's this horizontal line showing you 75% of the reds are large. And 25% of the greens are large. And notice this line, this horizontal line here now is lower than it was in the first rectangle. And that's showing you that only 25% of the green marbles are large. In the second jar of marbles, we have now a positive correlation between red and large. So with no information about the color and just looking at the proportion of large marbles total in this population of 100 marbles, the straight probability of randomly pulling a large marble from this second jar is 55 out of 100, or 55%. However, let's say that I'm in the other room, you can't see me, I'm going to pull a random marble out of the jar, and I yell out to you from the other room this piece of information. I pulled a red. Now in this case, my telling you that it's a red marble is important information. Now that you know it's red, you will change your original prediction about its being large. Remember, originally you were predicting 55% chance that it's large, but now that I've given you this extra evidence, it's counting as evidence, this piece of evidence that it's also a red marble, you are now going to increase your probability estimate, because now there's a 75% chance that this marble is large, right? 75% of the red marbles are large. So if you know that it's red, you're changing your probability estimate to 75%. In other words, learning that the marble is red is important information to you and has caused you to increase your probability about its being large. And notice we have a contrast between the proportion of large reds and the proportion of large greens. And because the percentage of large marbles among the reds is greater than the percentage or proportion of large marbles among the green, this means intuitively that large and red are properties that go together here. In other words, red and large are interdependent properties. Okay, finally, let's look at this third jar of marbles. In this third jar, down here, represented by this third rectangle, we find that 60 of the marbles are red, 40 are green, 65 are small, and 35 are large. 25% of the red marbles are large, while 50% of the green marbles are large. If I'm off in the other room randomly pulling a marble out of this third jar, with no other information being given to you, just given the straight numbers, because 35 out of 100 of these marbles in this third jar of marbles are large, then with no other information, then you would give the probability of my pulling a large marble from this jar 35%. However, if I yell out to you from the other room this piece of evidence, this piece of information, I pulled a red, in this case, it will cause you to decrease your probability estimate that I pulled a large, since only 25% of the reds are large. In other words, in this third rectangle, this third jar of marbles, red and large do not go together. in this jar. The percentage of large marbles among the reds is smaller than the percentage of the large marbles among the greens, and intuitively this means large and red are properties that do not go together. Now, in all these cases, we are thinking about correlation in a relative fashion. In the second jar, the second rectangle here, red and large go together more than green and large, and thus we get positive correlation. In the third jar, this third rectangle down here, large and red go together less than green and large, and so we get a negative correlation. And in that first jar of marbles up here, represented by the first rectangle, red and large are proportionately indistinguishable from green and large. So in all these cases, we're always looking at the one set relative to the other. So notice that positive and negative correlation is relative. For example, even if both red and green don't have many larges among them, red still has less than green, relatively speaking, so large is negatively correlated with red.